Hi, my name is Brittney O'Neill, and today I'm going to present about my data mining project, Associative Classification of Grocery Store Order Data. The outline of my presentation is as follows. First, I'm going to introduce my project, then I will briefly go over what associative classification is, and then I will talk about some related work. After that, I will focus on my project. I will begin with the dataset used, talk more about the algorithms implemented, go over the necessary data preprocessing steps, give the details of the model, talk about the hyperparameter tuning, and finally give an evaluation of how the model performed. Then I'll talk about the program I created and finish up with my conclusions and future work. After the presentations, I will give a demonstration of the program. So starting off with the introduction, this project utilizes grocery order data provided by Instacart on Kaggle. The goals are to classify the products in new orders as either reordered in the next order or not, to produce an understandable output, and lastly, create a program. This program can be used to visualize the variables used in the model, to evaluate the model, and to view the model output. This project is important because it will not only classify products, but the model output will be understandable so that it can be utilized to improve marketing tactics. For instance, if Instacart knows that bananas are frequently reordered, they could run promotions featuring bananas to encourage customers to make a purchase. With the new ease of storing data, it's really important for internet applications like Instacart to leverage this data into improving marketing tactics. This application will aid in just that. In addition, the program will be all-encompassing in that it can be used for data visualization, model evaluation, and the investigation of model output. So talking about what associative classification actually is now. So in order to classify products and get a model output that was easily understood, associative classification was chosen as the type of data mining classification algorithm to implement. This classifier combines two commonly known data mining techniques, rule association analysis and classification. The difference between traditional rule association analysis and associative classification is that in associative classification, you're only searching for a subset of rules that imply the class of the predicted attribute. So you're looking for rules in the form of what is shown in the bottom of the slide here. The left-hand side of the rule is referred to as the con set, which in traditional rule association analysis is often called an item set, and then the rule as a whole is referred to as a rule item. Associative classifiers have two main parts, one to perform the rule set generation and another that performs the classification. In this project, two different types of rules were created. General rules, which were created using the entire dataset, and customer-specific rules, which were created using only the given customer's orders. Two different types of rules were made to help increase the usefulness of the model output and to improve the predictive power. The general rules are intended to give Instacart an idea of what the buying patterns of all the customers combined looks like, while the customer-specific rules are generated to uncover each specific customer's buying patterns. These rules could aid in things like customer-targeted marketing. So that's just a brief overview of what associative classification is. So moving on to some related work. There are quite a few different variations between associative classifiers, and these variations are usually between the rule set generation algorithm or the classification algorithm. One proposed by Hadi in the paper A New Fast Associative Classification Algorithm for Detecting Phishing Websites attempts to reduce the computation time by employing a method called diffset to generate less item sets. In this method, the data observations which do not support the rule item are tracked. In this associative classifier, classification was based on multiple rules, and a modified version of this algorithm was used in the work, the classification algorithm, that is. Another algorithm that tried to reduce the number of item sets generated was proposed by Chen in the paper A New Approach to Classification based on association rule mining. And this algorithm information gain was used to help determine what item sets to merge in hopes of generating a smaller number of item sets. And this algorithm performed better on average based on accuracy than a C4.5 classifier. The paper shown here by Anasi at the bottom was a paper that actually analyzed grocery store data. In this paper, however, they performed traditional market basket analysis. An a priori-like algorithm was used to generate item sets, and once that was done, the rules created were clustered, and then a support vector machine was used to predict for new observations. The first two steps of this algorithm were repeated, and for this reason, this type of algorithm wasn't used in this paper. The Instacart dataset had a lot more attribute classes or products than the dataset used by ANASI, so running this type of algorithm would have resulted in a really large computation time. The algorithm in this paper uses an a priori-like algorithm to do rule item generation. This was chosen to try to uncover all of the frequent rule items for the classification. And then the classification algorithm mentioned above by Hadi was actually modified and used in this analysis to include both types of rules created. So now what I actually did and the results I obtained are going to be discussed. So starting off with the dataset used was provided by Instacart on Kaggle. It contained 6 CSV files that when combined contained 15 attributes. The attribute names and their descriptions are shown in the bottom table on the right. Some of the variables described the product ordered, the aisle in which the product was found. There was also attributes that described when the order was placed and so on. And then the top table there shows 2 example rows of data, just to give you an idea of what it looked like. And then Instacart actually split the orders into 3 evaluation sets: prior, train, and test. The test orders were used to judge the Kaggle competition and don't contain the value of the predicted attribute reordered, and as a result, this set wasn't used in this analysis, just the prior and train sets were. So getting into the actual algorithms now, first the algorithm implemented for rule set generation will be discussed. This algorithm was proposed by Liu and is called CBA-RG, which stands for Classification Based on Association Rule Generation. It's very similar to the a priori item set generation algorithm. One main difference, though, is that this algorithm creates frequent rule sets, not frequent item sets. There are 2 measures that are important in associative classification. Those are support and confidence. The equations are shown on the bottom left-hand side of the slide. Rule support is defined as the number of data rows that support the rule divided by the total number of rows, and rule confidence is the number of rows that support the rule divided by the number of rows that support the conset. This algorithm accepts 2 inputs, the data and the minimum support. The general idea of the algorithm is to generate candidate rule items. And then the generation of the rule items is done similar to the a priori generation of item sets. The similarity between the 2 is that the first k-2 items must match in order to merge 2 rule items. And rule set generation has the added condition, though, that the right-hand side of the rule must be the same in order to merge. Once candidate rule items have been generated, the data is gone through to find the support of the conset in the rule item, and then the rule items that do not meet the user-specified minimum support are removed, and finally, rules are generated. The generation of rules just removes any conflicting rule items. Conflicting rule items are those that contain the same concept but imply different classes. The rule item with the higher confidence is selected as the final rule. And this algorithm was used to generate the 2 types of rules that I spoke about earlier. Moving on to the classification algorithms, there are 2 main algorithms involved in this portion. Both of the algorithms used in this paper are based on algorithms proposed by Hadi. The first algorithm selects rules generated by CBA-RG to use for classification. In order to do this, the rules must be ranked. Rules with less attributes are ranked highest. If 2 rules contain the same number of attributes, then the rule with the higher confidence is ranked higher. If all of this is the same, then the rule with the higher support is ranked higher. If there's still no difference, then a rule is just chosen at random. Looking at the top algorithm, first, the algorithm first ranks the rules according to the system just described. It then goes through all of the rules, and for each rules, it will find all the training data rows that can be classified by the rule. If there is data that can be classified, then the rule is added to the final set of rules, and the training data classified by the rules is removed. If the rule can't classify any data, then it's discarded. This loop will continue until there's no training data left or all the rules have been investigated, whichever comes first. And now moving on to the prediction portion. The prediction algorithm has been slightly modified to incorporate the two types of rules created. The first step of this algorithm is to find all of the rules that can classify the new row of data. And then the rules for both customer-specific and general rules that classify the row have to be found. That's those first two lines there. Then the number of each type of rules that implies each class attribute is found. So in this case, attribute classes are reordered or not. After this, the score for each class is calculated. The score of a class is equal to the support count of customer rules plus the support count of the general rules multiplied by a user-specified weight. A weight was included to help improve the predictive power. The thought behind it is that the customer-specific rules should have more of an impact on the classification than the general rules. The customer-specific rules are more likely to be correct when predicting for a given customer than the general rules. The changes made from the original algorithm was the use of a weighting factor and the incorporation of the two types of rules. Looking now at what pre-processing had to be performed. The only pre-processing step that is required is to discretize any continuous attributes. This is done because rule associative classifiers can only accept discretized data. The attributes in this dataset had to be discretized were order, hour of day, and day since prior order. Order, hour of day was discretized using equal frequency discretization with 4 bins. This nicely split the data into kind of logical bits. So hours 0 through 5 represented a late night order, hours 6 through 11 represented a morning order, hours 12 through 17 represented an afternoon order, and hours 18 through 21 represented an evening order. And then day since prior order was discretized by converting it to week since prior order. And once this was done, the modeling algorithms could be implemented. And this implementation was done completely in R. So now getting to the actual modeling details. The prior data set was used to tune the hyperparameters, and then once the values had been selected for those, they were used to train the final model. So the train set was predicted on to evaluate the accuracy of the classifier. The attributes included in the model were department ID, aisle ID, product ID, order day of the week, add to cart order, the discretized hour of day, and the week since prior order. So now that I went over the details, let's talk more about the hyperparameter tuning. The hyperparameters had to be tuned were the minimum support for customer rules and general rules, as well as the weight used in the scoring function. To tune the hyperparameters, the prior dataset was split into another train and test set by customer. So for example, if a customer had 10 prior orders, the first 9 were part of the prior training set and the 10th order was part of the prior test set. The prior train set was used to train 8 models that had various hyperparameter values. The values used are shown in the table below. The prior test set was then predicted on and the accuracy was calculated. So looking at the table shown on the bottom of the slide, you can see that the third set of hyperparameters gave the best accuracy and thus were chosen as the values to use in the final model. You'll notice the largest value of support used for customer rules was 0.1 and the largest value for general rules was 0.2. Some larger values were investigated, but they caused no rules to be generated, so they're not shown on the table. Once the hyperparameters tuned, the final model was created, and then this is the evaluation metrics from that final model. The accuracy of the final model was just over 63%. This is better than random, which is good, but it's hard to judge the quality of this though. because a classifier can only be as good as the data it's classifying. Looking at sensitivity, the model does a good job of correctly classifying reordered products, but on the other hand, the specificity indicates the model does a poor job, still better than random, of classifying not reordered products correctly. The reason behind this could be due to the fact that there are so many more items that are reordered than not reordered. The result of this is there being more rules that imply reorder, which would lead to more unknown rows being classified as reordered. The bottom two tables show examples of rules that were generated by the classifier. Looking at the second general rule, this says that if a product was ordered from the fresh fruit aisle, it is likely to be reordered. And then looking at the first customer rule, we see that if this customer ordered lime flavored sparkling mineral water, they are with 96% confidence going to reorder it. And typically the user generated rules or customer generated rules had higher confidences than the general rules. Also, the customer specific rules tended to contain more products. And this is likely because people tend to buy the same products again and again, meaning the customer specific rules could meet the minimum support requirement. In the general rules, there's such a wide variety of products ordered that they rarely meet the minimum support requirement. So I will now give you a brief overview of the program and its functionalities. The page shown at the top of the slide is used to visualize the attributes in the model. The purpose of this was so that the user had an idea of what was contained in the data that went into the model. This page also allows the user to specify what attribute they would like to investigate. And then looking at the middle page shown, it displays the evaluation metrics of the classifier. This page gives the user an idea of how well the classifier performed on the given data. The final page is an example of one of the rule pages. These pages are used to investigate the rules produced by the classifier, and these pages are where a lot of the knowledge can be discovered that could really benefit Instacart. Okay, so conclusions and future work. In the end, a somewhat accurate classifier was produced. More importantly, though, the output of the classifier was easy to understand and displayed in a program that made it super easy to investigate. Furthermore, the runtime of the program was not unattainable. All these facts mean that the output of this project was very successful. But looking to the future, it would be interesting to run various other models on the data to get a better idea of how accurate the classifier actually was. Another idea would be to investigate other rule ranking systems. The one chosen caused the final rules to be almost entirely one item concept rules, so it would be interesting to see how a different ranking system would affect that. Lastly, I think there are some modifications to my code that could be made to decrease the runtime even further. But overall, I think the project was very successful. So here are some of the references, well, all of the references that I used for my project. And now I will move on to a program demonstration. So quickly switching over to R, you'll notice what I have pulled up here is a file called Project Master. This is contained in a program file that contains all of the R code that I created. And this Project Master file will call all of the other files in order to pull data, create the functions, and so on. So looking at these first two files, these will pull the data and merge the files. Then the second two perform some exploratory analysis, such as investigating the missingness and looking at some correlations. So this file will discretize those two continuous attributes, order, hour of day, and day since prior order that I spoke about in the presentation. And then looking at the next three files, these call the files that create the rule generation algorithm. It calls and creates the function that performs the classification. And then this one actually creates a kind of wrapper function that calls the rule generation and the classification and actually performs the associative classification and predicts on the new data. And this is actually what takes the most time to run. And then once the hyperparameters were tuned, the final model was created. And then this preparing data file was created for the purpose of putting the rules into a more understandable form so they could be displayed in the application. Now, from this file up has already been run. It takes about 5 hours in total. Like I mentioned before, the hyperparameter tuning is what takes the most time. And then the final model also takes about 30 minutes. So each run of the algorithm takes roughly 30 minutes. So I will go ahead and run this line of code that will launch the app. So you see the application will appear in a separate window, and the default screen is the Attribute Visualizations tab. So this is the tab that is intended to be used by analysts to understand the data used. And you see we've got this drop-down list on the left-hand side of the page where you can toggle between the attributes. I'll go ahead and click on Department. So since department is a categorical variable, a bar plot is shown. And for instance, if I was an analyst, I could look at this and say, oh, okay, so produce is the most commonly ordered from department. And then if the variable is continuous, a histogram is displayed. So moving on to look at the classifier evaluation tabs. So on here, on the left-hand side of the page, you'll see the evaluation metrics. So you've got your accuracy, error rate, sensitivity, specificity, and then on the left-hand side, or the right-hand side, you'll see the confusion matrix. Sorry, the left-hand side of the page has the evaluation metrics, and the right-hand side has the confusion matrix. But this page is really designed for the analyst to get an idea of how the classifier performed, what classes it's correctly classifying, which ones it's not, and if it's not classifying them well, what is it actually classifying them as? And this just kind of gives the user an idea of how well the classifier did. So moving on to look at the rule output, starting with the general rules. So looking at this first column in the table, you'll see this is where the rules are stored. And the first item in the rule, so looking at this first order, week since prior order, that's the attribute. And then what's next to it is the attribute value, so the attribute class. So the first order says, if week since prior order has a value of first order, then it's not reordered, which makes sense because if a person hasn't placed an order before, then none of the products can be reordered. But looking at the second order, we can see that, okay, if ILID is fresh fruits, then the product is likely reordered. And then you can come over to the second column and look at the rules support, and then one column further, and you can look at the rules competence. And you can actually sort the table based on rule support or rule competence. The tables are all already sorted by rule competence and decreasing because of the ranking system. And then some other functionalities of this page are you can toggle down here at the bottom between different pages of rules, and you can also come up here to this top left-hand side and show a different number of rules on the page. Okay, so now moving on to the customer-specific rules. So the table displayed here is the exact same as the previous table. The only difference on this page is that you can actually specify a customer ID. So anytime you enter an ID, the table is going to update to show their specific rules. So I'll go to 17, which is the one that I displayed in the presentation. So looking here, you can see all of the rules generated for customer number 17. Again, we've got this, if this customer orders natural lime sparkling water, it's probably reordered, and that's with 96% confidence. So this page is really just created for the idea that if an analyst wanted to know what products the customer commonly reorders or anything like that, they can use this page to determine that. So in general, the rule pages are just to try to help with the investigation of the model output and hopefully help with marketing tactics and things like that. So that's just a demonstration of my program, and I hope you all enjoyed my presentation, and thank you for listening.